Every day, over 1 billion liters of wastewater is generated in our region. UBC contributes about 10 million liters per day. The Iona Island Wastewater Treatment Plant alone processes over 207 billion liters a year before it's discharged into the Strait of Georgia. Can you imagine if all that wastewater flowed untreated right back into our water system and ocean? Common household waste, such as soap and food scraps from carburetors, would certainly be abundant, but not nearly as potentially harmful as the thousands of different chemicals that could be present in liquid waste from research laboratories. Without proper care, these potential wastewater pollutants can have a major impact on the environment, public health, and the infrastructure that is designed to transport it safely. Considering how dependent we are on a healthy water supply, being vigilant about what we dispose of as wastewater is extremely important.
สวัสดีครับ Greeting from Thailand. Good morning, good afternoon, and good evening whenever you are in this world. Today, my team would like to present our project, the fabrication of novel electrode developed by modified graphene oxide with alcysteine deposited on iron nanoparticle for enhancing the electricity generation of microbial fuel cells. Here is what we're going to talk today. We're going to start from the background and move to the methodology. And next, we're going to discuss our result that we get from our innovation. And the last thing is the conclusions of our project. Nowadays, people in the world are facing with the big and disastrous problem, which is wastewater. Wastewater going to be serious and serious in the future, and it's destroying many sea life creatures and deteriorating the world. More than 25% of the water sources, such as river and ocean in Thailand, is wastewater. Moreover, we cannot deny that the electricity is one of the necessary factors that we use in our daily life. But some countries, for example Cambodia, still have the news that they shortage of their electricity in some places in that country. As I mentioned that we are facing with the problem of the electricity shortage and wastewater pollution. So my team would like to be the exchange agent to see and solve those problems by creating the innovation that with the concept, livable planet, green area, and sufficient resources. And we hope that our promising innovation will be the innovation that can change the society to be a better place for the future generation. Start with the background. First of all, I would like to explain about the microbial fuel cells. So as you can see in the photo, in the picture here, it is a microbial fuel cell which composes of two sides. The first one is the anode as the left side, and the second one is the cathode as the right side. So the basic principle of the microbial fuel cell is utilizing the microbes to produce the electricity by the cellular respiration process of it. As you can see, when the microbes have a cellular respiration process, they're going to create the electron, and the electron will move from the anode side to the cathode side, so we can generate the electricity. However, the electrode in nowadays doesn't exhibit a high efficiency to trap the bacteria and high efficiency to conduct electricity. So we designed to synthesize the new electrode, which is alcysteine deposited on iron nanoparticle grafted on graphene oxide. Let's start with the first one, alcysteine. Alcysteine is one type of amino acid that contains sulfhydryl group, which can pass through the cell wall of the bacteria. So we use it to trap the bacteria. And then we use the iron nanoparticle, which have the positive characteristic on its surface to trap with the negative characteristic of the bacteria. And then we grafted it on our template, which is graphene oxide, which have the high ability to conduct electricity. Let's move to the methodology part. The methodology part comprises of 5 steps. The first one is synthesis part, the second one is characterization, the third one is electrode fabrication, the fourth one is microbial fuel cell construction, and the last one is tasting part. Here we come to the synthesis part. There are two main synthesis parts. The first one is the synthesis of graphene oxide, and the second one is the synthesis of L-cysteine functionalized on iron nanoparticle. So the synthesis of the graphene oxide starts with the bamboo, which is the agricultural waste in Thailand, and then we burn it, we ground it, we synthesize by using chemicals with the hammer methods, and finally we will get the pure graphene oxide. The second step of synthesis part is the synthesis of L-cysteine functionalized on iron nanoparticle. We start by using the iron colloid and mix it with the L-cysteine, and then we adjust the pH of it, and finally we will get the L-cysteine functionalized on iron nanoparticle. After we receive the graphene oxide and L-cysteine functionalized on iron nanoparticle from previous process, we mix it together with the magnetic stirring for 12 hours at room temperature, and finally we will get the final products. Moving to the third part of the methodology, we coat the ordinary electrode by using our final products by the polymer called P.PSS, and we will receive the novel electrodes. And then we construct the microbial fuel cells as you can see in the photo here. The anode chamber we add wastewater and using the novel electrodes, which we already synthesized. And the area between the cathode and anode, we use rubber growth as a membrane. And the cathode chamber, we add tap water and using stainless steel as an electrode. For tasting part, we have three kinds of tasting. The first one is electricity production efficiency. We taste by using the multimeter to measure the voltage and current. The second one is wastewater treatment efficiency. We measure the before and after of the COD value before using and after using the microbial fuel cells. The third tasting is bacteria absorption ability. We culture the bacteria which are Bacillus subtilis and E. coli, and then we utilize our novel electrode and see how the bacteria catch and the concentration of the bacteria before and the remaining while using the UV with spectrophotometer and scanning electron microscope.
Next is the results and discussion. Results into two parts, which is synthesis part for many characterization and testing part from test the ability of MFC using our sample. For synthesis part, first, SEM can confirm that there are graphene oxide sheet and also iron nanoparticles on graphene oxide. TEM also confirmed both of them too. From EDS result, we can see that there are carbon and oxygen which come from graphene oxide, and nitrogen and sulfur from L-cysteine, and iron from iron nanoparticles. All the elements are dispersed all over the graphene oxide sheet. From FTIR result, the peak can confirm many functional groups from graphene oxide and also from L-cysteine, such as amine group and sulfide group. The XRD peaks can confirm a crystalline structure of both iron nanoparticles and graphene oxide. D peak and G peak from Raman spectroscopy shows the crystal structure of graphene. Next is the testing part. We use SEM and adsorption tests to test both physical and chemical bacterial adsorption. First, for the bacterial adsorption ability, we put our electrode with our sample into each bacterial solution. By using UV with spectrophotometer at 600 nanometer, the concentration of bacteria when using our electrode has decreased significantly more than the control one for both E. coli and Bacillus subtilis. SEM results also suggest that after washing, there is still having some bacteria on a sheet of graphene oxide for both positive and negative gram-bacteria. An FTIR can confirm the presence of sulfide group and bacterial cellulose. And the setup potential of L-cysteine graphite iron nanoparticles in bacterial solution is decreased significantly from the control one for both B. subtilis and E. coli. These results can be concluded that our novel electrode can actually trap the bacteria. For the electricity part, we measure the current produced from the actual MFC using our novel electrode compared to the normal graphite electrode for 48 hours in three conditions, which are broad, E. coli, and wastewater. here is how we calculate the Coulombic efficiency, which is the efficiency of producing current per 1 unit wastewater treatment. In wastewater, you can see that our novel electrode has the Coulombic efficiency of 0.84, which is 4 times compared to the graphite electrode. Here is the overall result of what we had been measured for 48 hours. You can see that in wastewater, the max current of our novel electrode is about 7.6 times compared to the graphite electrode, and the max voltage of our novel electrode is 550, which is 3.9 times compared to the normal one, and the power density is about 28.5 times. Lastly, for the wastewater treatment, the results suggest that our novel electrode can actually treat wastewater by decreasing chemical oxygen demand values for almost 54%. In conclusion, modified graphene oxide with LCCE functionalized on iron nanoparticles was successfully synthesized from bamboo. The synthesized powder was coated appropriately on graphitic electrode as electrodes for using in microbial fuel cell. Both negative and positive gram bacteria can be trapped by LCCE grafted iron nanoparticle on graphene oxide electrode. Novel microbial fuel cell exhibit high electricity generation, which is 4.2 times Coulombic efficiency, 28.5 times power density, high bacterial adsorption ability, and high wastewater treatment efficiency.